we will finish it on the right time. So today the first lecture was the Professor Jengdo, but in the last lecture that was mine and he took that one for 2 hours. So I would like to make some tentative arrangement so that we try to cover all the components which are available here. So today topic is about the metabolite qualitative analysis, but for the metabolite qualitative analysis we have to start with the basics of the chromatography and try to understand how these metabolites we have to quantify in any chromatography. So there are a few PowerPoints, you will find out they are very basics and they help us to understand the concept of the chromatography. And then we try to understand the different peaks, what are the different parameters which is responsible for some changes in the peaks actually. So yes, this is the first part that I want to come here. So I am starting with the basics here, and basics are just like what are the different type of the chromatography. So whatever you are using GC and the MS, these are the different type of the chromatography. But before that we use the thin layer chromatography, and because thin layer chromatography, it was the paper chromatography. So there is a advancement come in the chromatography with respect to the time, and now we are these techniques is evolved enough that we can separate the two small metabolites which are present in the microgram in any sample. So what are the different types of the force which is responsible, and how we use the different chromatography to utilize the force, sample holding force to analyze their sample. So you can find out this LC and the GC, they are using basically two concepts. First is the stationary and second is the moving phase actually, mobile phase. So there is an equilibrium between the stationary and the mobile phase of the different metabolites, and these metabolites are interact with each other by using these 4 different type of the specific methods. And gas chromatography, in which we are using the gas as a mobile phase actually. So this type of the equilibrium is basically exists when we are using any metabolites that we need to separate actually. So if you go back, you will find out that what is the thin layer chromatography. So I will quickly finish because these are the basics for all of you. So thin layer chromatography is just to identify any substance and which is used to assess the purity of the compounds. So you know it's a very cheap process, and it's just it can be used anyway here. So to purify any components we are using the TLC, and a very small quantity of the metabolites is required for this task. So TLC is very easy actually for all of us, and TLC is basically using the disturbing the two and the different substance when mixed together. So they are the two phase in which these metabolites can dissolve actually. That is the stationary and that is the mobile phase. So this stationary and mobile phase is stationary can be defined as any adsorbents which you put it on the plates, and the mobile phase is the another phase that is basically diluting liquids which travel along the stationary phase, and it carries all the metabolites along with. I am just helping to know basics of the TLC so that we are able to quantify those metabolites very well. And these components of the sample can be separated because of their interaction with the stationary phase and the mobile phase actually. So how much amount of the components is absorbed on the stationary phase versus how many are dissolved in the mobile phase. So this is the basic concept actually. What metabolites is coming at the what time actually, because how much it is dissolved at a particular time in the stationary and the mobile phase. So that's why this thin layer chromatography come in the picture, and it is very simple in the illustration. So I am just covering this for you. This is very simple. Now you try to understand what is the concept here. So concept is very simple. You can see there is a components and you are putting the another components. So now this is the another component. These are the 3 different components and they are moving along with each other. So you can find out one move very fast, second move very slowly actually. So what force is responsible for this particular component? So you can understand the TLC. So TLC is just like a plates, and this is the picture of the TLC. So this is the best thing you can use in your labs also to quantify the different metabolites. And yes, it can be, if you are using the standards and you can understand the peak, so you can identify a particular component that is present or not present. The second, you can find out the adulteration in the different samples also. Third, the first of all, before in the metabolomics, you have to do the TLC and find out some solvent which can cover those metabolites actually. And this is very cheap process. If you know the profiling of the metabolites on the TLC, so you will get the confidence, you can purify your components and can structure elucidation can be carried out in the NMR also. So this is something very useful for all of us. Now I am coming on the another, how you prepare the sample. So those are the basic concepts you can find out during the graduation and other things. So I am not covering these parts too much. I am not taking so much seriously this part, because these are the just you can do what is the pipeline, how, where you put, these are the 10 standard AU candidates, these are from the graduate level. But question is come up that these notches, what is the concept, how these capillary tubes move these samples from the bottom to the up actually. So that is the major components we have to cover here. So you try to understand that there is some force, and these force equilibrium established, and there are few different types of the physical interaction which is responsible, which allows some components to move first, another components to retain them up to a time. So they come later on. Now second point come in this TLC, how you identify these sports actually. So sports identification is another components, you can use these components. So if sport can be seen, so you can outline them with a pencil, and if sport is not able to see it, then you can use some other visualization techniques, that is the UV plates or the UV lamps also. And sometimes we are using some chemical components also to use organic compounds which can be used for this particular detection process. Their purpose is also. So commercially made plates are available. So just purchase a packets of the plates and isolate your sample, extract and try to understand is it coming on that particular along with the standards. If you are getting some sport along with the standards, so your most of the problem is resolved here. So now, because if some sample are the colorful, so it's okay, but some sample are not colorful. So for that we have to use the another techniques, that is the we have to use some chemical components. So these are the chemical components of the different classes. So if you are using the alkaloids, so you have to go ahead with the drag and drop reagents. If you are working in the glycosides, so you have to go ahead with the antimony trichlorides. If you are going with the sugars actually, so you have to go ahead with the alanine phosphates. And if you are working in the amino acids, so you have to go ahead with the ninhydrin. So these are the different visualization agents which you have to use according to your work actually. So another part is that how you interpret the data of these things here. So basically we have to go ahead with the retention factor value. Each sport has its own retention factor. Sport means that analytes actually. So that analyte has a specific interaction with the stationary and the mobile phase. On the basis of that, this RF value was calculated actually. So this is something. So same phase and using the same mobile phase, you can find out the same component has the same RF under the same extraction protocols. So however, RF value can be compared to those of the unknown substance to add in their identification. So this way you can identify your components very well. So this is the very ordinary process, but it can give a better message actually. So you can understand these are the RF is a distance from the start to the center of the substance, distance from period of the solvent. So you have to RF calculate the value, everything has a RF value actually. So RF of the 3-4 different samples are the different, but they have the distance. Middle part we are taking as from here, this is the RF, this is the total. So it is the unique with respect to that particular metabolites or particular analytes actually. So I am coming with another part, that is this is the most effective way to identify the components actually into sports any substance. Authenticity is another component next to the unknown substance on the same plate. So this way you can identify your analytes very well. In addition, you can go ahead with the purity of the sample, which can be estimated from the chromatogram. So anybody can understand that chromatogram is nothing actually. It is the it can give us the running tracking of the movements actually, how the mobile phase and the stationary phases are interacting with each other and how these analytes are moving across that particular column. So if you are getting any graph which is representing the movement of the analyte, so that is that we represent as a chromatogram. That is the chronography picture of the chromatography actually. So you can find out an impure sample basically give more than one different type of the spore. So you can easily say that this is the pure, this is the impure components. In principle, basically, these components are differ with each other in the solubility, in the strength of their absorption to the adsorbent, and that's why their substance behave differently during their movement actually. So these are the applications of the TLC, that is the identification of the chemical purities, identification of the compound, and the examining of the many reactions. So if you are doing the reactions of some specific, in another class I will take the MCA. MCA is a little bit difficult, but I try to cover those portions in which we are just estimating the different reaction in a cell actually, in a particular pathway. So for that we are using the TLC. So TLC is a basic routine that we are using. So there is an advancement come up in the TLC, that is the HPTLC. HPTLC is the high performance thin layer chromatography. It gives the advancement of the TLC. It has very good separation efficiency and automation of the loading of the sample. Running time is very low, and it can offer the simplicity, solvent choices we can do. It is very precise, speed and the economy. So HPLC, this is the difference between the HPTLC and the TLC. So today I arrange your half an hour visit to the NMR also and HPTLC also. We have the HPTLC here also. So whenever we are doing the metabolomics, so we started from the TLC, then we come on the HPTLC. HPTLC is giving just very small amount of the separation. It can give the separate up to 3 to 5 micrometers also. And you see the thickness of the layer, so better thicken, less thickness means more fine particles which are using as a adsorbent media actually. So solvent is also used less, and it is automatic spotting the sample. So this is something that is here coming here. So paper chromatography is the another part that come up here, but I cover this in the here because there is so many variation. On the basis of that, this column chromatography come up. So this paper chromatography is using the concept that is the partitioning coefficient, and here they are using the filter paper that is a carrier inert supports actually. So this factor separation of the mixture of the solutes or filter paper in the partition between the two different immiscible phases actually. So now molecules need to decide how much time these molecules need to retain in the mobile phase, how many they retain the separation phase also. So this is just like a media here also. So many cellulose fibers are used as a stationary phase, and the second is the organic phase, that is flowing the sample on the paper. So this is something that is the solvent. So solvent is coming from this way, and this paper is hanged. So there is so many variation in the paper chromatography, depends on the arrangement, direction, as well as the way you are putting the from where this mobile phase is moving actually, from the center to the outer, from the outer to the center, from upper to the left, and sometimes two-dimensional chromatography is used in this paper chromatography. 2 dimensions, we run the sample in the 2 dimensions. So basically there is a partitioning after between the mobile phase and the stationary phase, which is bound with the cellulose, and you are getting the isolation of the component. It depends on the coefficient of the solute actually. So now we are moving towards the components which are responsible for these fast and the quick movement and the slow movements. That is labeled here as a partitioning coefficient. So partitioning coefficient is something that can be defined by this concept actually. So K is equal to C bracket stationary, K is multiplied by the mobile. So it represents the concentration of that metabolites that is at a particular time, that is present in the stationary phase and that is present in the mobile phase. So this ratio is giving us a value actually, that is labeling as a partitioning coefficient. So partitioning coefficient is a component which defines how much metabolites is present in the mobile phase, how much metabolites is present in the stationary phase. So try to understand, this is a general procedure, so I am not quickly I want to move from, because general procedure is not, I will give the slides actually, but so we have to cover because many slides we have. So these are the 5 and the 6 different stages of this general paper chromatography, but yes, you have to cover in the stepwise manner. Finally, you have to detect your compounds is present or not compounds. And after detection, you have to identify what is that compound actually. So this is something that is given. So there are so many techniques come up here, and they depends on the types of the papers. So you can find out this is First one is the radial development, second is the descending development, third one is the ascending development. Radial development means you are separating your chemical, you are putting at the center and they are spreading just like a radial. So it gives the better separation of the metabolites. And second is the descending means you are putting your sample at the top and they are moving from the lower part, they are moving upward, and in some cases they are moving from the upward to the lower also. And this is the filter hanging, so you are putting sample here, they move here, they are moving from the top to the down actually. So these are the ascending, this is the ascending, this is the descending, and that is the radial actually. So another thing is the multiple chromatography. So sometimes you have to use the instant chromatography integrated approach also to identify a particular metabolite. So multiple development means you have to develop the multiple chromatograph which are repeatedly developed in the same direction, and thus the complete resolution of the two and the more substance which have a different RF value which can be easily received by this one. And yes, so look here, we are using something that is two-dimensional chromatography. Sometimes it is very difficult to separate a metabolites from the another one. So you have to change the solvents, you have to change the direction of the movement of the solvents also, and you are getting in a, that one direction is perpendicular to the next direction. So this way you can develop a 2D chromatography, and finally different type of the solvent system you have to use for the different run actually. So this is something that is also useful in the fashion in the laboratory condition. For the if you are from the college, so you have to start from your metabolites analysis from these small techniques actually. So look here, I am here. So there, yeah, this is the component. Now this is the single one component. In 2D we are moving this component. Now the same components will change their perfection, and now they are moving. So you can do this thing, and finally you are getting two metabolites which are not yet not separated by the one dimension. Now they are separated from the each other actually. So now paper chromatography, we started from the PLC, and paper chromatography was a medium, so it was not giving the better resolution in many cases. So there is another advancement come up, that is the column chromatography. So in the column chromatography, what happening actually, we need a column, and this column is just like some components, stationary phase is packed in this column, and the mobile phase is moving through the gas and the liquids, and that's why according to the different type of the CC, major type of the column chromatography is distinguished from each other. One, on the basis of this chromatography, we are using this type of the CC, column chromatography is a media in which you have to pack your stationary phase. So on the basis of that, these are the different type of the chromatography. They only come up when column chromatography was come up, in which we use the different stationary phase as well as the different mobile phase, and they are using the different mechanism also, remember. So on the basis of that, you have to go ahead, so we can separate the molecule with respect to the different components, and these different molecules are just like the molecules separate from each other, and just the smaller size enter the pore, then larger molecule passes through the column, there is special type of molecule. It is what I So column chromatography is easy, but now it is used for the enzyme isolation basically. So when you are using the live enzyme, so yet this is in the fashion, and for the purification of the native enzyme, column chromatography is still used in all the medical sciences laboratories. So you find out here, and this is the definition of the different components we have to discuss here, starting with the solvent, developers, effluent, eluents, elute, and the retention volume. Retention volume is a time that was consumed by analytes when during the training, entering in the column and exit from the column actually. So now I am coming with the packing. Open column chromatography is just like the open mobile phase under the atmospheric pressure. So in the open chromatography, open chromatography still used in many laboratories actually. So they are using to isolate the different proteins actually. Protein purification, they use this chromatography very well. But here there is no force you are implementing from the outside. It is under the atmospheric pressure. एक और दे दो चेयर ना, ये सोफा लगा दो. So now there is another points come up that yes, some metabolites are taking so much time for the column chromatography. Open column chromatography is required 24 hours, 46 hours, 36 hours. So now there was ready-made columns come up in the market, and yes, there was an issue is that sometimes we have to make the different type techniques are used to produce the different type of the columns actually. So because there is air bubbles, so you need to avoid those air bubbles. So for that we have to go ahead with the sample application. So sample applications, yes, eventually there is no so much synchronized movement of this right from here to there actually. I'm not able to see over here good reflection. So here sample you have to use always the equally soluble molecules of any particular sample, and yes, if you are using the concentrated in the one length, so please use the same concentration in the another length. Otherwise it's very difficult to identify the real thing. So when you put your sample, so it must have the same concentration, whatever sample you are using. And yes, this is the elution techniques. How elution techniques means that how we have to send the mobile phase in the column actually, solvents. So they are the two different methods, that is the isokinetic elution and the gradient elution basically. Gradient elution is further classified into the two different categorized segments. The first is the continuous and second is the incontinuous. That is, you can say that is a stepwise. Actually, I will come on the points where from we have to start our basically. So because these are the basics, so I have to start from the basic. So detection you have to do. Doing the detection you can monitoring the elusive fractions using specific detectors. So first is the elution, second is the detector. Whatever the peaks is coming, you have to detect those peaks specifically. So for those peaks you have to use some detector, and this detector can use some physical properties of those solvents which can be used to amplify and convert into the signal, so that you will get some signal and you can identify those peaks are due to those particular analytes actually. So these are the different factors and they have the different effect. You can see here, so these are the different factors, and try to understand every factor is influencing the different effects here. So starting with the particle size, every metabolite has the different particle size. Second is the column dimensions, whatever you are using for the GC and the LCMS. Then what is the packing actually? So packing also influences many things. If you are not using the uniform packings and there is an air bubble, so you will get the different peaks at the different retention times. Column temperature is another point. If you are increasing in the column, so diffusion come up in the picture, and finally you have to take care of the uniform temperature for the uniform running. Then eluting solvents, solvent flow rate, continuity of the flow, condition of the adsorbent, and the concentration of the solutes. These are the another factors which are also playing the critical role for the separation of the different components. Finally, you have to take care of all these parameters to improve the resolutions. Otherwise, you will get something different here. So yes, now picture is coming here. That is the number of the theoretical plates. Every column we have to make some imaginary plates here. These imaginary plates is giving us, we have to calculate how many number of plates are possible in that particular column. So here N is the number of the plates, H is the theoretical plate height, L is the length of the column, and this HCTP, that can decrease efficiency of the column actually. So whatever the theoretical plate heights we assume, if length is high, so it reduces the interferences, the resolution of the separation. So we have to use minimum size of the height plate, theoretical plate heights, then we will get more number of the plates. And when we will get the more number of the plates, so we can go ahead with the better resolution. So these are the two different columns. One has many plates and second has only few plates. And because this plate has less number of the heights, it has more number of the heights. So this is associated with the resolution. So basically there are the theoretical concepts come in the picture when you have to understand the differential migrations. So differential migration is a phenomena by which the speed of the different compound in the mixture can be determined by the number of the molecules of that particular metabolites are present in the mobile phase. So our target is that maximum components must have to present in the mobile phase so that it can give early peaks of the detection basically. Some compounds come too late because they interact with the stationary phase, and that's why they require the time to come up with the mobile phase with the passage of the time. So that's why differential migration is come up. So let me explain this differential experience moments with this picture. So you can find out there are the two phases. One is the mobile phase and second is the stationary phase. So molecules are moving less with the stationary phase, more with the mobile phase. So they come first actually. The second metabolites has more affinity with the mobile phase and the less more with the stationary phase and the less with the mobile phase. So those metabolites come later actually. So this way, you can understand which compound is coming first. The compound, the peak of any analytes come first, which has more solubility in the mobile phase as compared to the stationary phase. And the latter components come later actually. The other components come later because they have more interaction with the stationary phase. So this is something which can understand by using this mathematical equation. In this mathematical equation, U is the velocity, Ux is the velocity of the materials, R is the fraction of the material which is present in the mobile phase. So we use Ux is equal to Ur, and then if you can, R value is 1 and the 0. So if R value is the 1, so all the molecules come along with the mobile phase. If R is the 0, so molecule never come out of the column and it retained by the stationary phase. So this R value must be in between the 0 to 1, then only these mobile phase, these compounds come within the running time. Sometimes you are saying that you are running the components, but that metabolites is not coming in the column actually, in the chromatogram. So there are the two reasons that we have to play with this R value, that only we have to find out it. So we have to change the solubility, we have to change the column, we have to change the solvents also, and running condition, temperature also, so that sometimes those metabolites detach themselves from the stationary phase and we can pick them in the chromatogram. So this is the another factor other than the capacity factor is the another factor. So this factor controls the distribution of any material between the two competitive phase actually. So this is also labeled as a differential coefficient. We can use the another name, that is the capacity factor, and we can use the mass distribution ratio, that is the K. So K is the number of the molecules of the which are present in the solvent divided by the number of the molecules of that analytes which are present in the mobile phase. So is the total number of the mole of the compound in the stationary phase, and this is total number of the mole of the compound which are present in the mobile phase. So now this K dash is equal to TR divided by the T naught, that is again divided by the minus by the T naught and divided by the T naught. So this is the time actually. Time required for the sample to move through the column is, and T naught is equal to time required by the solvent. So you always find the difference, and this difference is due to these capacity factors. So better capacity factor means that mobile retained more in the stationary phase, while the less capacity factor means molecules are moving along with the, so move faster as compared to the other components. The second thing is about the movement of the material through the zone actually. So we have to discuss about the number of the height plates, and these number of the height plates, there is also an interaction between the different height plates actually. So different height plates means, first of all, molecules establish equilibration between the mobile phase and the stationary phase in one place, then another place, then another place. So this way they are moving the molecules, and we are using the height equivalent to vertical plates. So number of the plates is very important. More number of the vertical plates means better separation, because more equilibrium was established between the metabolites as well as the stationary phase. So this can be represented by this equation. N is equal to L divided by the equation. L is the length of the column. So if you increase the length of the column, so more number of the vertical plates and more equilibration happens. So length can give us a better chance to get the better resolution. But you know, this is how to decrease the HTP. So how we decrease the height of the different plates in a column. So we can reduce the height of the different plates in the column by doing decreasing the particle size of the stationary phase and proper selection of the good mobile phase. So you have to take care of these two things. Only after that you can reduce the height of the number of plates, and then you will get the more number of the plates means more equilibration come up, and more easy resolution better resolution you will get. So I will explain this thing in this method. So here it is starting with the 32 compounds, but then it is divided 16, then 68, 16, 8. So this way, when this molecule enter into the new plate, so there is a new equilibration come up. So finally here you are getting, this is the final thing. After that, this thing component from each other. So n is the number of the plates which can give us the narrow peaks actually. So peaks are the most important for us. This is the another point you try to understand. This number of the plates is the 5, number of the plates is the 25, number of the plates is the 150. Here it is the 5, 25 and the 150. So try to understand what type of there is a merging happening in the number of the 25s. 150 means you are getting the better resolution. In the first A and the B, they are integrated they merged with each other, metabolites actually. So it is not when you get the peak, so they merged with each other. But in the second case, if you are increasing the number of the plates from the 5 to 25, so you are getting 2 peaks, but they merged in one in between that. But in the third, if you are increasing more number of the plates, so you can find out 2 different separate peaks actually. So this is how we increase the number of the plates. So this was the points actually. So now you can understand we can increase the number of the plates by decrease the particle size of the stationary phase and by selection of the appropriate mobile phase also. So you have to go ahead with the method developments by using such type of the practice. So particle size, how can you decrease? So particle size we can decrease in the column because we have to use the ready-made column. So particle size is not a bother for us, but you have to find out which type of the column you are using for your work actually. So flow rate is a major issue actually by using the high pressure pumps. So if you are using porous particles, so they will make the more resistance in the column, and that's why if you are using very fine uniform packed particles, so it will get with the pressure they are moving simultaneously. So column are basically made up of the stainless steel, and they are only just 7 cm about if you are going ahead with the HPLC and the UPLC. But if you are working in the GCMS, so in the GCMS this column has a very big in length actually. It's around 50 meters sometimes also. So another point is the absorbent activity, then uniformity and concentration of the mixtures. We have to take care. Second point, as I told you about the selection of the mobile phase. So we have to find out what type of the metabolites you want to do with your work actually. If you are working with the polar metabolites, so you have used the different solvents. If you are working with the non-polar components, so you have to use some organic solvents. The rate of the flow is also matter actually. So if you are moving everything, just push the meta in the column. These columns are very small. They have small a uniform packing, and there is no air passage in between them. So whatever the compound is entered into those columns, so they must have to go ahead with interaction with the stationary phase actually, mobile phase. So now mobile phase is entering very fast or very slow, so there will be no equilibration between the mobile and the stationary phase. So that's why you have to make this thing in a proper way so that you will get the narrow bands. Consistency of flow is another parameter. You have to take care that there is a continuous flow of the mobile phase during the extraction process. Now are the factors due to the column. So column dimensions are increasing the length of the column improve the separation. However, they usually lead to the slower flow rate actually. So we can increase the column length because more column length means more number of the plates, more number of the plates means better resolution. But we can't increase the column length up to a limits actually. So that's why we have to maintain a particular fixed column length. Second is the column temperature, so you have to maintain this column temperature very well. So this is the instrumentation that of the HPLC. These are all the different things. Column is here in the blue color. This column is the blue color, and here are the detectors, so you can use. This is the basic instrumentation of the HPLC. If you go with the real HPLC, so this is that type of the HPLC. Here you can find out the column is again, it's only 7 cm here. You can find out here. So this is the HPLC, and what are the solvent filters? You have to use the different solvent filters to remove all the impurities. So different impurities can be removed by using the different filters which are present in the solvents. So we use some solvent pre-column filters also. इसमें ना मुझे बैटरी चाहिए एक्चुअली. Those impurities choke the column, and sometimes they create the problem so that you are not getting those things properly. So to improve the column, we have to use the vacuum degassing, and vacuum degassing means we have to remove all the air bubbles which are present in the column actually. So now what are the factors of the solvent delivery systems actually? So the solvent delivery system has the three fixed things. What is the solvent you are entering into the column actually? So the first, you have to activate in the constant flow that you have to use. Second, accurate mobile phase composition. Third is the force that you are giving, it must be uniform actually. So these are the three forces you have to use. So pump is another component which create enough force so that this solvent can enter into the column actually. So pump are here. Then another one is the injector. So these are the different phases that we have to use. That is the normal phase, and then second is the reverse phase. So these are the different type of the stationary phase that we have. Many times you know that we have to use a column that is the reverse phase. So this column is based upon the what type of the stationary phase you are using for your work actually. So normal phase we are using the silica gel, but for the reverse phase we are using the silica gel C18. So C18 is basically we are using for this work actually. So this is the peaks, and you can identify the compound A, compound B, and the compound C. This is the point of the injection of the column, and this is something that you have to find out the compound C. So these, after injection, these compounds move from here and they come up to here. Now the point come up that the qualitative and the quantitative analysis with the chromatography. So retention time is a thing that you, if you are working with HPLC, if you are working with LCMS, so you have to use the parameter that is the retention time. So this retention time is a highly characteristic parameter of the solutes for a particular condition basically. Therefore, it can be used to identify that particular solute. And it is based on the quantitative analysis is based upon the comparison of with the height and the area of the peak analytes with of the a few or more standards, and the conditions are controlled properly because these parameters height and the area vary linearly with the concentration of the solids. So whatever the chromatogram you are taking, just like this one, so you have to calculate the two things. First is the height and second is the area. Only then you can do it. So peak height is something. Peak height is the height. Basically, if you find out in the ideal condition, peak height are just like a perpendicular length coming from the top to the down actually. You never find anything else. So this measurement can be done ordinarily. It is the distance from the baseline to the top of the signal peak. So you have to calculate the peak heights, and the parameters of the HPLC quantitative analysis is the first thing. We have to common parameter for the compound is the retention time. So this is the retention time you have to calculate of each and every metabolite. These are the different peaks, and these different peaks at what time it is coming. So this from the 0 up to here, it is the retention time of this analytes, and from 0 to that one, that is the retention time of the another component. So now another points come up, that is the resolution. Resolution is an important component which resolve the two things with each other. So resolution value of 1.5 and the greater between the two peaks will ensure that the sample component baseline separated to a degree at which the area and the height of its peaks can be accurate very measured. So I am explaining here. So these are the two things which can be resolved very well with each other. So this is a parameter that is labeled as a resolution. So resolution is calculated under using the separation two peaks. So this is the formula of using the RS is equal to TR2 minus TR1 divided by the WB1 plus by WB2 and then divided by the 2. This is the another method that is also used for the resolution basically. So T is the TR1 and the TR2 are the RT of these two one, and WB1 and WB2 are the widths of the two different parameters. So when you do these things, so use the sidebar, you can find, you can separate from each other. So you must calculate the total width and the height of a particular peak. If two peaks, you will get the clear picture of the separation, so you will get the resolution. If this value is less, so there is an issue, otherwise it will give a very good resolution. So this resolution itself depends on the three different parameters basically. The first is the saturation parameters, second is the efficiency, and third is the retention. So selectivity is based upon the separation factor, and the retention is based upon the capacity factor. So totally, if you go and find out the calculation for the resolution is defined here. The resolution is depends on the efficiency, selectivity, and the retention, these three parameters. So how you understand the selectivity and the selectivity, retention, and the efficiency? So this retention is a time that is used when this peak is come out from the detector detect that peak, and selectivity is how much they separate the two different analytes from each other, and efficiency is helping to know the middle height, total heights and the middle heights of those things. So these three have the different parameters. Efficiency is based upon the number of the heights, selectivity is based upon the alpha, and this retention is based upon the capacity factor. So if you understand these points, if you understand these basics now, so you will understand LCMS and the GCMS very well, and you can develop your methods also. That is the most important.
Sir, how is speed theory?
Speed theory, okay, no issue. Speed theory मैं तो ये सोच रहा था मेरे पास ज़्यादा है, मुझे speed से चलना पड़ेगा. बाद में करा देंगे, जितना होगा 20 मिनट में धीरे करा देंगे. So now the another points that comes here is the retention factor. So I will explain these three factors now. What is the efficiency, what is the selectivity, and what is the retention. So you come understand that this retention is a capacity factor that is labeled as a K. K, it is a mean of measuring the retention of the analytes in the chromatographic peak actually. How much time is used by that stationary phase to retain that metabolites in a column actually. So that is labeled as a capacity factor. So here I am explaining a chromatogram. You can understand that it has inject time. So this is the first value and this is the second peak. So these two peaks have the different retention time, and one peak, whatever the coming very close to the peaks, they have less retention time. Whatever the peaks which are coming far away from the zero, they have more retention time. It means they have more capacity factor value. So this high K value and the low K value we can define by using this retention time. TR divided by the T naught divided by TR minus T naught and then divided by the T naught. This is a very simple to understand actually. So retention capacity factor is giving us how much time that metabolite is present in that column. So there are the several ways to determine the T naught also, and the TR we can calculate very well, but how you calculate the T naught actually? So T naught you have to calculate by using some specific standards also, like uracil, hexane, and a few components also, other metabolites also. If you know these two values, so you can say that this metabolite has this retention factor and it is coming as a separate peak itself. So I am helping to know how the different component influence the retention factor. Many times you are listening that my retention factor is here, but I am getting a peak little bit far away from that retention factor. So if you increase the organic solvent of the mobile film up to the 10%, decrease the K for each component by 2 to 3, just try to understand. Altering the mobile phase composition. Mobile phase composition is a very powerful separation tool to use to optimize the HPLC separation. So sometime if you change the mobile phase composition, you will change the RT value also, capacity factor also. You have to manipulate too much this capacity factor during the method development. So here I am explaining the things very well. So here this K value is the 14.4. The P6 has the K value 44 actually. But this is on a particular standards when we are using the different composition. Mobile phase B percentage, different composition. So largest gain in the resolution in come up when K value is present in between the 1 and the 5. If K value is below the 10, so it will be very difficult for you. If K value is coming then the 1, so again it's very difficult to resolve a single peak. But if the K value is in between the 1 and the 5, so you always try to find out whatever the mobile phase composition you are using for your experiments, so that you will get the K value in between the 1 and the 5. So K value before the less than 1 is unreliable actually. That is not possible. Above the 5 it creates the when many issues and too much retention best values come up. So more complex mixtures, K value will be extended up to the 10 and before the 2 basically. So the second points that come up with the alpha, that is the separation factor. So this separation factor is the ability of the chromatography system to chemically distinguish different sample activity. Separation selectivity means they select one compound to the another compound. So you are getting one peak due to the one component only, not due to the two different components. This is usually measured in form of the retention factor of the two peaks in question and can be visualized as the distance between the apex of the peak. So here you can see the picture of this chromatogram. So chromatogram means whenever you are getting the running peak, they are as a chromatogram. So here you find out the two different peaks, and this separation factor is equal to K2 divided by the K1. K2 is that is the retention type based upon total divided by the 0, and K1 is TR1 minus T2. So high alpha value indicates good separation power and a good separation between the effects of the each peak actually. So by using this method, the selectivity is always greater than 1. Remember that. So that alpha is equal to 1 at least. The peaks can be correlating. If the selectivity is greater than the selectivity, further you will get the difference. Here I will explain this thing. So now, how you change the separation factor? So separation factor can be changed by changing the organic solvents, nature of the organic solvents, mobile phase pH, solvent strength, and additives, stationary phase, and the temperature. So you can manipulate many things to play with this separation factor. So the mobile phase pH can have a drastic effect on the selectivity of the separation, especially when acidic and the basic analytes molecules are present. Small change in the pH can bring about a large change in the retention factor behavior of many peaks. For this particular separation, it would be difficult to identify a single pH value. So that's why if you change little bit now, you are getting the peak somewhere because the K value is changed actually. So this is a change of the organic solvent actually. So if you are using the organic solvent, in the first case it is the 40% KCM, in the second case it is the 50% mid-mole. So if you change, here you are getting the two peaks here very clear in this solvent, but here they are getting the merged peak. In the another case, these are the merged peaks, they are giving better resolution in the mechanism. So if you are using the different solvent, so you will get the totally different patterns also. Sometimes they are okay, but sometimes they are not okay. So you have to use many different solvents to finally find out which solvent is giving better coverage of the metabolites of your own interest. Remember, always try to create your own interest, then you are able to do this thing. So this is another point that come up. So let me take an example of the pH here. So mobile phase pH 5.1, mobile phase pH 5.2. According to it, it's a 0.1 difference. But try to see what are the difference coming in the pH chromatography. So in mobile phase pH 5.1, you get the 5 different peaks, but here you are getting the 5.2, 5 and the 6 peaks are the merged actually. So a little bit change, and it's very difficult to monitor such type of the change basically. So a 0.1 unit is enough to separate the two peaks, and 0.1 unit is enough to merge the two peaks as a single peak. So there is another example of the solvent strength and the additive. So solvent strength and the additive, sometime in the mobile phase we are adding some chemical, okay, some solvents. So here sulfonic acid concentration is the 57 millimolar, here it is the 60 millimolar. So only just 0.3 millimolar is increased, and you see how many are here. Here are only 6 peaks and there are only 7 peaks. So sometimes if you are working casually, you are not working very precisely. So you are what never reproduce. Remember, you have to take care of each and everything and be precisely do your work. Then only you can resolve. Sometimes you are saying that my peak come, then it never come again. So first time you work unfortunately, but then you are trying to play with the small parameters and you never get the peaks. So that was a reason that you have to think about this type of the genuine concern to separate the two different peaks. So this is another example. Here you can find out the two different column actually, which has the little bit different solvents. So same components here, but you will find out here this 1, 2, 3, 4, 5 peaks are present totally separated from each other. They are little bit very close. That is the 1, 2, 3, 4 and the 5 4 and the 5 are not able to separate here in the lower panel, but in the upper panel, upper part of this panel, you can find out 4 and the 5 they are separated from each other. So sometime if you are using a different column also, so maybe those can give you the better separation of a particle peak. Here you will say that 4 is a peak. But in the upper case, 4 and the 5, they are going to the two different energies, which are coming at the same time. So you have to play with you have to change the retention time of the metabolites with respect to by showing their interaction with the other components also. So column temperature is another important point. Column temperature, what happening here, you can find 3, 6 and the 5. Only just concentrate on the peak number 3, peak number 5, peak number 6. But if you go with if you change the temperature from 22 degrees Celsius to the 44 degrees Celsius, so what you are getting? You are getting 3 somewhere and 6 come before to 5. In another case, it was behind the 5. So these peaks can change from their position also, their number also. If you change the temperature and everything else. Sometimes if you are not taking care of your machine, if you are not taking care of the solution, if you are not taking care of the maintaining the temperature and the pH and gradient solvents, and if you are using little bit high and the low additives in the mobile phase, so you will get always the different result. And you will be highly frustrated. So what should you do? So always try to use the appropriate and precise. You do small work but be smartly, so that your work can be reproduced. And most of the issue in the PhD students are coming here that they never work smartly, they are working very casually. So their work is not repeated in the most of the university. So labs means your work should be reproduced. If your work is not reproducing, so you are working very casually. So see another here, that is the effect of the selectivity on the resolution. So selectivity that I told you about the alpha. So see here resolution. Change selectivity has a dramatic change on the chromatography resolutions, and yes, 1 and the 2 you can see here, they are the 1 and the 2 selectivity, and this is the formula that we have to use for the selectivity, that is the alpha minus 1 divided by the alpha. So efficiency of the column column we can go ahead with, we can explain this concept by the two different theories also. How much this column chromatography can be explained, efficiency of it. So I have very limited time because Professor Jain will come after 5 minutes. So I will show you the just equation actually. As I told you, there is a equilibration come with each and every plate. So this is the equation that is used for the band spreading actually. These bands can spread. So if you are using all the parameters rightly, so definitely you will get the single peak. So plate height is another concept. So that I told you. So this is the plate height value. This is the normal distributions of the plate heights. And this is the experimental of the number of the plates in the column actually. So these are the number of the plates which are present in that particular column. So by using this equation, you can calculate that how many number of the plates are present in that particular column. So variable which affect the column efficiency, there are many variables. That is the flow rate, that is the band broadening, depends on the length of the time in the mobile phase, in the contact with the stationary phase. A greater amount of the solid diffusion also gives that longer time of the residence. So flow rates, we can't play too much, increase up to a limit. So we allow the time actually, how much we time would like to these solids interact with the solids which are present in the mobile phase, interact with the stationary phase. So column efficiency can be increased by decreasing the particle size. We can lowering the viscosity also of the mobile phase, increase the temperature, also giving the bad, reduce the bad broadening. So you know many times you are getting the bad broadening. So these are the parameters which can be used. So column efficiency is, they are the different way. We can decrease the column diameter, decrease the sample size, controlling the capacity factor, selecting appropriate stationary phase also. So these are about those different components we have to take care. If you understand the rate theory of the chromatography, so rate theory of the chromatography, I am not able to cover here, but rate theory can easily explain the bad broadening concept in the hair. So you see, these are the few reasons, that's why you are getting the bad broadening, and this bad bread of the bed increases through the column actually. So shape of the chromatographic peaks is affected by the rate of the elutions also, and that broadly is directly proportional to the residence time. Residence time means how much time those solutes are present in the column. So this can be explained by the Venn diameter equation for the plate height. So this is another way by which we can understand the rate theory. So I'm not going to explain this much, but yes, I want to. This is another thing that I want to show here. So this is the band broadening here. You can understand this is the zone of the solid which is moving along with the diffusion. What happening? They diffuse too much, and now this becomes the too much band is broad. So when you get this peak now, so this peak from this way, not the single. So you have to take care of the longitudinal diffusion also, that is explained by the eddy diffusion method. So there are many other things we are not covering, but yes, this one is major. Sometimes these two things, in the station, in the mobile case, they are moving very slow. But in the another case, it is moving fast, it is moving slow. So that's why you are also getting the bad broadening. So many bad broadening come up due to this way. So there is another point, that is the resistance to the mass transfer. So better we have to skip these few slides, but I have to understand this concept. So whatever the metabolites which are entering in the column, they are using a path actually. Sometimes some metabolites are using the small path, some are using a large path length. So here this peak is okay. Three metabolites are just entering at the simultaneously, but one is coming first. So if you are getting such peak now, so this type of the path length is also occupied. Here it is the 3, it is the 2, and it is the 1 actually. So this way you are not getting the appropriate peak while you are getting the bad broadening also. So this rate theory concept, you can understand all these points. So what are the alternative of the height equation, that is the Knox equation. So I am just Gidding equation is another one. So we are not explaining those things, but yes, this is a column actually. So column is made up of the many ways. Some metabolites enter into these particles inside. These are the area by which these molecules move from one place to another place in the column, and that is the flow, depends on the flow. So these are the different parameters you have to take care of your work actually. Starting with the participant coefficient, retention time, capacity factors, relative retention, plate height, number of the plates, and the resolution. So you have to understand these parameters. If you know these parameters during the method development, so you can easily quantify your metabolites. So this is the picture by which you can understand. If you are playing with the K, and this is the concentration which is present in the stationary phase, concentration present in the mobile phase. So if it is moving on the right directions, so you will get these peaks in the signal idle head. But if K is increased, so you will get the overloading. If K is the decrease, so you are getting the tailing also. So K, this type of the tailing and that type of the overloading can be manipulated by you playing with the K value. So this is all about, I think, this class. And yes, I used a few things, and it was just before the metabolite quantitative analysis. You know a little bit about the different parameters you have to manipulate, and so that you will get the better resolution of the single peak. And the single peak resolution is based upon the 3 to 4 different parameters. So you have to take care. Many thanks to Gyan and all the participants who listened it very sincerely. And I would like to acknowledge the Central University of Punjab, the Ministry of Education also for this course also. Now, Professor Jain, we have to take 5 minutes break. Okay. So there is a 5 minutes break, and after that I arrange that mic for all of you. Then we are able to go ahead with this course. This is to mute color 5 minutes break. 5 minutes mute color. Yeah. Okay. एक तो हाइट आपको दो काम करेंगे, एक आइडेंटिफाई करेंगे, एक क्वांटिफाई करेंगे. ठीक है. आइडेंटिफाई करने के लिए टू if you are working the LC and the GC, or if you can work with the HPLC, MS is not a part of it. So you have to use the standards. But if you attach MS with those HPLC and GC, UPLC, then we try to give the fingerprint, mass fingerprints of that particular metal. So for that, there is a library. They can identify what is the mass fingerprint, the fingerprinting pattern of the particular metal. So on the basis of those library, they can identify probably this is that metal. But if you go ahead with the quantification you have to cover the area that is present in that particular Now you have to use the different chemometric colors. So whatever you saw me now that is the another thing is that you have to use the chemometrics to visualize your data. So that they are associated, this area is associated with the concentration of the metabolites which finally come in the elutions. Because there is some detectors, so those detectors giving you those area actually. So area is present in a very, if you are using some standards also, so you will calculate this area is corresponding to this particular standards also. So sometimes you can use this strategy also used to find out the exact concentration. So basically if you are working on the targeting, so you have to go ahead with the concentration also, quantification also. Otherwise, first of all, you have to identify your metabolites. And you get the metabolites, whatever the table you have. Now you have to use the chemometric tool basically directly. You have to go ahead with the PC flow. You have to go ahead with the loading pattern. You have to go ahead with the OLSPD. Then you can find out, okay, if you are getting the metabolites from the same category, or the same class, you have some biology actually. What is the meaning of the biology here? When you set up your experiment, so you have to clearly decide that what type of the information you want to generate. How you capture that information, this is the second point. So if you know that you are working on the only sugar and you are looking at the sugar molecules, how they behave differently when this temperature increase in the blood. So you have to only focus on the sugar molecules. So now the another things come of the temperature, another variable. So you will set up your experiment with many temperature sets. Then in the chemometrics, you have to display that our whole experiment was based on the temperature with respect to the elevation or down regulation of the concentration of the different sugar. So now in the chemometrics, you know one variable is the temperature, different temperature. Another is the sugar molecule. So you just show those things, you will find out. If you use the heat map, that's also good. Otherwise, you have to go ahead and identify the VIP score, variable factors. So that is also a good thing. So this 4 of the 5 figures are enough to present that this is the components. These are the different metabolites which are given some specific characteristics doing some specific chemical या biochemical या cellular process. तो वो आपका काम आपको उससे आगे ये करना है. तो रितु को मैंने बोला है कल मेरी एक क्लास है, मैं इसको 15 मिनट की लेके इसको पूरा कर दूँगा, है ना. तो ये आपको ये बताएगी कि हमारे पास ये we received a file from the LCMS and the GCMS. How could we go ahead? So it will be very simple. Maybe you will understand or not understand, but that is useful for all of you. आगे ऐसा. So now we are starting the another lecture. It is from the Professor Jengde. There is a little bit change in the brochure actually. We started that we will cover this portion, but a mismatch come up in the first day itself, and now it is continuing. So we are confused. If we start with the more complex thing and you are not getting the simple things, so it will be just like nothing for you. So we are trying to cover all the portions. MCA metabolic control analysis, I tried. Network analysis was another component. We missed that one. MCA I tried to cover afternoon, and it will be some mathematical equation are also present in the mathematics. But if you understand the basics of the MCA, that's enough for you. So Professor Jain come here and he is, yeah, please. What is the issue of the benefit? This depend on that.